In this chapter, I'm going to show you what NoSQL databases are all about. There are several reasons why NoSQL has become so popular over the last few years, and one of them would be the need to handle big data. In other words, the need for scalability. We'll be looking at the difference between integration and application databases, and why relational databases might be better for integration databases, but for application databases, well, you can choose the best tool for the job. I'll introduce the term polyglot persistence. This is using multiple databases within the same application. And finally, there are lots of different types of NoSQL database available. We'll be studying 3 of them on this course, so we'll look at the major types. As a starting point, we'll look at what relational databases offer. You don't need to know about relational to study this course, so I'll start with a very quick overview of the basics of relational. So, in a relational database, the data is stored in tables. The tables have columns, which are effectively fields, and every record is stored as a row in the table. And a really important feature is that we define relationships between the tables. Relational databases support a defined syntax for reading and writing the data, and that's known as the structured query language, or SQL, sometimes called SQL. But relational databases are just one way of storing data. And in this course, we're going to be exploring many other ways of storing data in a database. The phrase NoSQL, well, originally I think was a bit of a provocative term to say, hey, we're getting away from SQL. But in recent years, the term has been made a little friendlier. It's been retrospectively changed into an acronym which stands for Not Only SQL. And the reason that the industry have moved towards calling this Not Only SQL is in recognition of the fact that these databases that we're going to study are alternatives to relational databases, but not a replacement for SQL databases. They're an additional resource that might give better performance or be easier to use in certain circumstances, but in no way a replacement to the traditional SQL databases. In this opening chapter of the course, I'm going to look at why these alternatives to relational databases might be needed, and to start to think about when each of the different types of database might be a suitable choice for a particular need. We'll then develop these themes further as we progress through the course and go into more detail on different types of NoSQL database. We'll start the journey by looking at the limitations of relational databases that NoSQL databases are intended to solve. There are 2 generally acknowledged problems with relational database, and the first one is that of scalability. And by that I mean creating a database that can support really large amounts of data. A term that's being used a lot in the industry these days is called big data. And that's just in recognition of the fact that many applications now have to deal with far greater amounts of data than we were traditionally used to. You might be thinking in terms of the big internet real estate, such as Facebook and Twitter. You can imagine the kinds of data that they have to deal with day in, day out, much bigger than a traditional enterprise application might be used to. One of the reasons that we're having to deal with more and more data is simply the fact that we're able to store more and more data. Check out the very informative Wikipedia page on big data. At the time of this recording, there's a really interesting graph here, which I'll just click through to. And this is describing the massive growth in information storage capacity across the globe. And if you just look back a very small number of years, you can see there has been a very recent explosion in the amount of data that we can store. And that means that we need new techniques and new approaches to not only storing the data, but processing the data as well. So even the smallest organizations are capturing massive amounts of data, maybe their websites' log files, or maybe minute information about their customers' movements and behaviors. So don't think of big data as being something that's exclusive to the likes of Wikipedia, Twitter, Facebook, and Google. In general, when we want to store more data in any kind of database, we really have two choices as to how we can do it. We can either increase the size of the computer that we're holding the database on, and that means really the data storage, such as a hard drive, and memory capability, and possibly the CPU as well. Or we could have multiple computers, each of which is relatively small in its capabilities, but combined together becomes a powerful combined resource. This first approach is called vertical scaling, and it will work for pretty much any system. And it's simple. You just need to buy a bigger computer. But that does present problems. Having a computer with huge amounts of memory and storage space is really expensive. If you wanted to double the amount of capability that you have, it's going to cost much more than double the cost. It's going to cost exponentially more. So if we can scale by adding more physical machines to the pool of servers working together, then that's going to be a cheaper option. This second approach is called horizontal scaling. And I think it's helpful to introduce a couple of terms that we're going to be using quite a lot on this course. And it's really two different forms of horizontal scaling. And that is replication and sharding. Replication means that the data has been copied or replicated between multiple computers, so that any individual data item exists on more than one machine. So replication provides a fail-safe against data loss. Sharding means that the data has been split between multiple machines, so that no one computer will contain all of the data. And sharding is one way that we can achieve horizontal scalability. So we can divide up our massive data set, which is good, but the problem is this is going to be less reliable. If computer A were to catch fire, then we would have lost 1/3 of our data. So in reality, for a database to be truly scalable and reliable, we'll need it to support both replication and sharding. So one of the reasons that you might be looking at using a NoSQL database is some of them are very good at both replication and sharding. But before we look at the NoSQL databases, I'd just like to look at traditional relational databases and ask ourselves, can they be replicated and sharded? Well, most production relational database systems, including Oracle, Microsoft SQL Server, and MySQL, can support replication, but they generally don't support sharding. So, in other words, they're not really horizontally scalable. It is, in theory, possible to build a horizontally scalable relational database, but to do so would be a really challenging problem. And the reason why it's so challenging is because of the relationships between tables. Suppose we have a system storing customer information, and we might have a schema that looks something like this. We have a customer table, but we also have some supporting tables, such as this location table. Well, if this were to be sharded, and we were to have the customer table on one computer and the location table on another computer, how would we be able to link the two tables together? if we wanted a query that joined the data in those two tables, then, well, because they're on separate computers, that would not be an easy task to achieve. So relational databases, just because of the way they are inherently designed, are generally not good at horizontal scalability. But don't get me wrong, it is possible to shard a relational database. There are at least two big well-known examples out there in the industry. Wikipedia use MySQL for their data storage, and they make heavy use of sharding. However, as far as I can tell, their sharding's quite simple in that they effectively shard by language. So one database stores all of their English pages, another database stores all of their Arabic pages, another database stores their Spanish pages, and so on. That's a very simplistic form of sharding. It's almost as if they basically have completely separate databases. And that would be relatively easy to implement because any page request is always going to be going to one and only one of those databases, so the results won't have to be combined. And another example is, until recently at least, Google used to use MySQL for their AdWords software. Their AdWords software is responsible for a lot of their revenue. But again, they were very, very careful to deeply simplify their data structures. I haven't gone into detail of the schemas that they had, but as far as I can tell, they were using very simple tables that didn't have constraints and didn't have relationships with other tables. So they were using MySQL as a very basic data store, which made it much easier to shard. So the point of that digression is, please don't misquote me, it is perfectly possible to shard and horizontally scale a relational database, but it's really hard to do it, especially if you're using any of the features of a relational database. But many of the NoSQL databases that we're going to see do attempt to address this problem. And they do that in the way that they store their data. And it's really nothing more than the way they store their data is often far simpler than relational databases. So if you're coming from a relational database background, you may well be surprised and disappointed at some of the databases we're going to study, in that they are far less capable than relational databases. But bear in mind, the reason for that is a compromise so that it's easier to scale the database. So apart from scalability, I would say the other drawback of relational databases is relational databases are not always a good fit for the data that you're working with. Because relational databases have been around for a long time, relational databases tend to just be the default choice of storage mechanism. You have a requirement to build a website, and before you've even thought about the requirements, you're installing a database like MySQL. And then you're finding throughout the rest of your development that you're trying to shoehorn your data into tables and relationships. And your data and requirements just might not be the best fit for a relational database. Tables and relationships might be the perfect solution for your application, but often forcing relationships and normalization into data structures won't necessarily be the right choice for all types of data and may well not give the best performance. We'll be seeing as we progress through the course that there is some requirements that would sit far more sensibly in alternative data structures. Now, really importantly, we're not trying to say that relational databases are old-fashioned and now we have all these modern NoSQL databases, we should leave relational behind. That's absolutely not the aim of the course. The lesson of this course is really there are alternative approaches to storing data, and every approach has benefits and drawbacks. There are some features of relational databases that you're generally not going to find in NoSQL. And I'd say the most important of those is the ability to define constraints. When you set up a relational database, you have the ability to say that a particular field must be unique, or must have a particular range of values, or it can't be null, or it must have a matching record in another table. And these kinds of constraints means that other developers who are using your data can't accidentally put invalid data into your database. So with relational, the database server can take the responsibility for maintaining the data integrity of your system, which is a great feature. But in NoSQL databases, usually those kinds of constraints don't generally exist. And certainly the 3 databases that we'll be studying on this course, only one of them has a very small constraint feature. Apart from that, there's nothing there. So with NoSQL, maintaining data integrity is going to be something that you have to control in the code that you write that interacts with the database. Which leads me on really nicely to one of the main aspects of why you might want to consider a relational as opposed to a NoSQL database. I think it's really important to understand what type of database you need for your problem. And it was Martin Fowler, a long time ago now, back in 2004, who coined the term integration database and a corresponding concept of an application database. An integration database is a data store that's going to be shared by multiple stakeholders. You're going to have an environment where multiple developers are all writing their own applications that will make use of a common data store. That's an integration database. And with an integration database, it's really important to enforce constraints to prevent the developers accidentally breaking the data integrity. This kind of database also needs to have a very rigid and predefined schema which can't be easily changed by the developers. Imagine what would happen if one developer started adding fields to a table that developers of another application are also using. It would be chaos because you might accidentally break the other applications that you have no knowledge of. And that's why with an integration database, relational might be a perfect fit because we can apply very rigid schemas and very rigid constraints. And typically, an integration database would be managed by a DBA, a database administrator. But an integration database might not be what you need for your application. There's the corresponding concept of an application database, which is a database controlled and accessed by a single application. It's not going to be shared. So the development team behind the application database has sole and full control of the data. So in this instance, you have the choice of whether you want the constraints to exist either in the database or in the code. In these instances, NoSQL databases could be the right solution. We often talk about the database as if there's just one great big monolithic database holding all the data for a company or a project or whatever. But for many systems, a more elegant solution might be to use multiple databases. You could have a system that uses a relational database, perhaps an integration database, but also would use 1 or 2 different NoSQL databases working within an application. And these databases would be doing the jobs that they're good at. Maybe you have part of your code which needs really high performance, and you can't get that performance from a relational database. These kinds of systems that use multiple database technologies are called polyglot applications, and they're becoming more and more popular as larger and more complex systems are being built. On this course, we'll be looking at 3 different NoSQL databases in turn, and I'm not going to complicate things by mixing them together, but it's a concept worth keeping in mind as you continue studying this course. For example, we'll be looking at a database called Redis, which is unbelievably simple. You can pretty much only store strings in there, and there are no tables, and often the data isn't even stored to a disk. So compared to relational, Redis looks almost useless until you realize that Redis can be deployed with precision to address just specific tasks that Redis is good at. Redis is good at speed. So that's why you might want to consider using a NoSQL database. But NoSQL is a very general term. It applies to a large collection of different types of database, all of which have different features. Now, we think there are at least 5 main types of NoSQL database. In this course, we're going to be studying 3 of them. The 5 types are called key value stores, document databases, graph databases, column family stores, and object databases. Let's look at each of them, and we'll start with the key value store. Now, key value stores work with very simple data structures. If you're familiar with the concept of a hash map in Java, then that's really what a key value store is. You add in as many data items to the database as you want, but each has a unique key. Now, key value stores are really easy to distribute over multiple computers using sharding. Because of the way the data is stored, there's no relationship, so it's not at all complicated to separate the data into multiple computers. And a really important feature of a key value store is lookups are really fast. And by a lookup, I mean searching for a value by its key. Doesn't matter how big the data is, it will always be quick to retrieve a single item using its key. So why would you use a key value store? Well, because it's fast and it's simple. They tend to be helpful in speeding up the performance of an application which might be being slowed down by the need to interact with other databases. It's useful for data that is going to have a reasonably short lifetime, such as a shopping cart for an e-commerce website. You might want to keep that data for, say, 30 minutes, but we don't need to keep it for days. And as we'll see later on, key value stores are perfect for that requirement. As with all databases, there are drawbacks, and the drawbacks to a key value store is that you can only retrieve data using its key. So there's no way to, for example, search for all of the values where the customer's surname matches a particular value. So you can say, for example, retrieve customer number 17, but you can't search for customers where the surname is Smith. In this course, we'll be using Redis as a key value store. There are lots of others available, but we think that's really popular, and all of the others work along the same lines. Next, we have document databases. The idea behind a document database is you can store a large amount of data, but in what we're calling a schemaless way. And we mean by that each record has its own structure, but no 2 records need to follow the same structure. Instead of thinking of data as being a table where every row has the same field, in a document database, each row or each element in the database is completely independent from the other elements. You can have lots of documents all with the same structure, or you could have documents with lots of different structures. The choice will be yours. In a document database, you can also store complex structures, and this makes it ideal for storing certain types of business data. For example, you have a customer, who might have a collection of accounts? Well, you could store the customer and the accounts as a single document. The accounts would just be embedded into the customer document. And because they're stored in the same document, they'll be stored on disk together. So you don't need any complicated and potentially expensive in terms of performance joins to combine the data together, because you actually store it in the database already joined. The reason for choosing a document database might be because they're ideal to store huge amounts of potentially complex structured data, and they're easy and efficient to scale through sharding. The flexibility of the databases is also a useful feature. If you have optional fields, then instead of having lots of fields with nulls, which you would have to do on a relational database, in a document database, you just leave out the fields that you don't need. So you don't need to know at design time the exact structure of the data that you're going to be working with. For the drawbacks, well, there are generally no relationships between the records in the database. Instead, we typically structure the data so that each record is self-contained. All of the data for a particular record will be contained within it. Now, compared to a relational database, this means that we often get lots of duplicated data. Document databases are completely denormalized. Of course, that can cause huge complications if you need to update data, as that data might appear in multiple places, and you'll need to work really hard to preserve data integrity. So don't get me wrong, these are huge drawbacks for many requirements. The sweet spot for a document database is where you're not worried about relationships, you don't care about duplication of data, but you want a lot of it. For this course, the document database that we'll be studying is called Mongo. And then there are graph databases. These are built on the basis that the relationships between different entities is more important than the data within the entities. The general description many people use is that if you can model your data on a whiteboard, then you can create it in a graph database. Now, I would say there are fewer uses of graph databases. These are much less general, but in the applications you have where relationships are the important aspect, then graph databases are beautiful to work with. A common example that people give is if you're working on a social networking application, then the relationships between your users, for example, is really important. And a graph database is perfect for that. But don't get me wrong, graph databases are not just for if you're working for Facebook or LinkedIn. They can be useful in many different applications, and we'll look at some of them on this course. So the advantages is that a graph database will allow you to write more efficient and neater code in some circumstances. And those circumstances are if the relationships are more important than the entities. And basically, if you've ever written code where you've had to do joins, lots of joins between lots of tables, then you might find that the same effect with the graph database is far more natural. Also, if you're writing a very heavy object-oriented model, then we find that graph databases sometimes map more cleanly to a graph database. The downside for graph databases is they're not a great place to store detailed information about the objects. It's far more useful for the relationships. And they're also less scalable because they're much more difficult to scale. Sharding is a lot harder on a graph database. For this course, we're going to be studying the database called Neo4j. There are two other types of NoSQL database that we're not going to study on this course, and they are called column family and object databases. Column families are very similar to relational databases. The difference is more of an implementation detail. The data is stored on the disk by column rather than by row. What that means is if you had a table something like this, physically on disk, the data would be stored something like this. Now, I am being very oversimplistic here, but I hope it gives you the idea. The data for the columns is stored together, whereas in a traditional relational database, the data is stored by row. Now, the advantages of this is it makes certain types of queries far more efficient. If you're doing a column scan, then the database doesn't have to do any jumping around on the disk. It can simply start from a particular position and run through all the fields for that column. It's also quick and easy to add new columns. If we want a new column, then under the hood, it will just append the data to the end of the data set effectively. Whereas in a relational database, it can be more complicated to add new columns in the implementation under the hood. But the main feature is the efficiency of searching for data within a column. And for some applications, doing fast column scans is really crucial. The disadvantages of column family databases is you need to know in advance how the data will be used to be able to define the schema for the database. So you really have to think very carefully about all the different types of query that you might need to run before you start. If you want to add in a new query later on, it might require a lot of data restructuring. And column family databases don't support joins, so you often have lots of duplication of data. We're not covering column family on this course, but the two most popular we think at the time of recording are Cassandra and HBase. And we might do a separate course on column family databases in the future if we think there's a demand for it. And finally, I'll just mention very briefly object databases. These have been around for many, many years now, but they were an idea that never really took off in a big way. The concept behind an object database is that it would automatically persist the objects that you have in an object-oriented application without the developer needing to do anything. So it would effectively act as a persistent memory for your application. You behave in your code as if you're working in RAM, but automatically the RAM is mapped to memory. The reason they haven't caught on, well, I think there are several reasons, but one big reason would be it's very difficult to use an object database as an integration database because the data storage format is always going to be specific to the programming language that you're working in. Because of this shift towards application databases and the fact that NoSQL is fashionable, it's possible that object databases might have a comeback in terms of their popularity, especially as all of the other NoSQL database types are becoming more and more used. So on this course, we'll be studying in detail 3 of those types of databases. Specifically, for our document database, we're going to be looking at the MongoDB, perhaps the most popular NoSQL database at the time of this recording. For the graph database, the most popular, again at the time of the recording, is a database called Neo4j. And the third section of the course will be key value stores, and specifically we will be using Redis, and that's a blazingly fast database that often runs in memory. So the course is in 3 sections, and it doesn't matter in what order you do the sections. So if you're particularly keen on graph databases, you can go straight to the first chapter that covers Neo4j. So any order you like, and at the end of the course we'll have a more advanced chapter which covers something called the CAP theorem, and this gives you more insight into the kinds of compromises that many of these NoSQL databases are making. So it's up to you where you go now, whether you want to do Mongo, Neo4j or Redis. They're all very different, certainly interesting. I hope you enjoyed the journey.